All right. So welcome. This is the IEEE 2310 Spring 23 final exam review. We'll be talking about MIPS and registers and processor design. And do you know, is your exam cumulative? Does anyone know? It is cumulative? Okay. So feel free to ask questions. If we have time at the end, you can ask questions about anything throughout, but most of what we'll be covering now is processors. So to get into it, MIPS is like a computer architecture that has its own instruction set. And so it has kind of basic commands, basic assembly type commands, where you deal with registers. Instead of setting up a variable and that variable has a name, you work directly with registers and immediate values. So some basic commands that maybe you've seen some of these: add, subtract, add immediate, maybe not the unsigned ones, but multiply and divide. And when you study assembly languages like MIPS, you start to see like the connection between the software that you write and what happens in the hardware and the flow of the bits. So that's why we study MIPS, is that you can see kind of at a low level what a computer instruction is doing exactly and how it gets executed. It's not magic. In fact, it's all very specific. It's all very directly coded into hardware based on the architecture. So these are some instructions. We'll come back to this maybe in a bit. And opcodes, you see, these are resources that are online. You can find this information online, and you can see like how the add instruction breaks down into the opcode and the other function and control bits. So there are different types of instruction in MIPS. Three main types. There's R type, I type, and J type, right? So an R type instruction, this is probably the most standard type instruction. This will be like your add and subtract, where you have pretty much you have two things that you're doing an operation on, and you're storing it into a third register. So the naming of these registers can be a little bit confusing, but we have, in general, it's the operation, and then there's $RD. This is talking about the destination register. And then your source and your target register maybe is what you call these. But usually what happens is you'll add, like if it's an add instruction, you're going to add the contents of T0 and the contents of T1 and store it into T2. So that's generally what happens with an R-type instruction. And we'll talk about specifically the register file later, but these registers, are just little sections in memory. We're using register files, which the processor can access very quickly, and they store a very small amount of data, but they can be used really quickly. So this is why they're used for CPU calculations. So if the add instruction, add T2, T0, T1, is really doing contents of T0 plus the contents of T1 and storing that into, the contents of T2. It's written in a little bit misleading way, but we'll see how that breaks down into bits. So every instruction, right, is really just a string of bits, because everything in a computer is either zeros or ones. So every instruction is going to be just a line of memory, of instruction memory, that gets executed on the processor based on the value of these bits. So we can break down these instructions into their bits using a couple of rules. First, the opcode. This is going to depend on the type of instruction. So if it's an add, it's going to be different than it's a subtract, or if it's a multiply. So the opcode talks about what function it is. Your registers, again, are going to be talking about which registers you're using. So in the MIPS architecture, in the MIPS world, I don't remember exactly how many registers there are, but usually you don't have to deal with many more than 8, I would say. And the registers are formed like this. They have a 0, 1, and then 3 bits describing which register number they are. So for example, RS is a 0, 1 followed by 0, 0, 0. So this is register 0. This is T0. 0, 1 followed by 0, 0, 1. That's a binary 1. That's T1. And RD is 0, 1 followed by 0, 1, 0. That's 0, 1, 0 is a binary 2. This is T2. And you can see that the order that they are in the bits is not the same as the order they are in the command. So that can be kind of confusing sometimes, where this is like the destination where the sum gets stored into. But then when we do it in bits, it's like RS plus RT equals RD, right? So don't get confused on that. I'm not sure if you get a chart like this on your exam, but if you can remember how to break down these R-type, J-type, and I-type instructions, you'll be able to do it for all of them. Okay, so when we're decoding this instruction, right, we have to get these register values in binary. The shift amount, I think we won't have to worry about this in this class. And the function code, again, has to do with the type of instruction. So it's an add, it's a 1 followed by all these zeros. And so in the MIPS architecture, each command is 32 bits. 32 bits. So every command is going to have a different breakdown of how many bits go to which field. And the registers are always going to be 5 bits. So for these R-type instructions, we have 3 registers. The registers make up 15 bits. 32 minus 15, we have 17 bits left. The opcode is 6 bits. So if we subtract out 6 bits, that's 11 bits. And 11 bits will go to the shift amount, which is 5, and the function code, which is 6 bits. So the breakdown is going to be a little bit different for each type of instruction, but within a type, within the R-type instruction, it's going to be the same regardless. So whether it was an add or a subtract, these bits are going to be different, but it's still going to be 6 bits for the opcode. And some notation that we use. So say that the instruction is this string of bits, 1, 0, 0, 1, 0, 1, 0, all the way up, and there's 32 of them. We usually call the least significant one bit 0, and the most significant one bit 31. So 0 to 31, you can prove to yourself that that's 32 total bits. And sometimes it's useful to index into an instruction like this. So if this is our instruction, and if we said, 31 to 26, we'd be talking about bits 31, 30, 29, 28, 27, and 26. Okay, so that's actually 1, 2, 3, 4, 5, 6 bits. Even though 31 minus 26 is actually 5. So don't get confused with the indexing. Make sure you think about if we're counting bits 31 through 26, that's 6 bits long. So the sizing is really important. So we use this notation if we're talking about a certain section of a command. And for example, the opcode is 6 bits long. So the instruction bits 31 to 26 represent the opcode. Okay? Similarly, if we're at bit 26 is included there, then the instruction from 25 down to, if we think about this, the registers each have 5 bits. So 25, 24, 23, 22, and 21. So 25 to 21 is your RS value. Okay. Similarly, you can break down the other ones, but understanding how this notation is how we talk about how we break up these commands, that's important. So yeah, this is an R-type command. We will do an example later, but this one, just make sure that you know the order of the registers. RS and RT are operated on, and the result is stored in RD usually. And RD comes first in the command, but it comes last when we break it into bits. So another type is an I-type or an immediate type. So this is where this is an immediate type. So this is where we type a value. So an example is like add immediate T2, T0, and 25. So what add immediate does is it says I'm going to store into the contents of T2, I'm going to store the contents of T0, plus 25. So instead of using a register that we're adding, register plus a register, we're doing register plus an immediate. We get to say whatever that immediate is. And whenever we introduce an immediate, we have to think about how much freedom does the programmer have. So you've probably written code before where you can set a variable to be any number you want, and you're really only limited by int max, the maximum value of an integer in your system. In this MIPS assembly language, our immediates are limited to 16 bits. And the reason is we break down the instruction again. The opcode needs 6 bits, and the opcode is going to tell us which instruction we're looking at. And really what the opcode does for the processor is it tells it how should I interpret the rest of these bits. You can see that the fields aren't the same as the R type. So if the processor notices that this is an I type opcode, an opcode that's associated with an I type instruction, then it won't go looking for a third RD register here. It'll know that there's 2 registers that I'm looking for, and then the rest of the bits correspond to the immediate. So that's how the opcode helps the processor determine how to split up the rest of it. And as for the rest of it, for an I type, you see that we only have 2 registers. We only have 2 registers this time, but we do have the immediate field. So if we have our 32 bits, then we take away 6 for the opcode, right? That's 26 minus 2 times 5 for the registers is 5 bits each. So that's minus 10, leaves us with 16 bits left for the immediate. Oops. Okay, so there's a couple of different forms, right? Add immediate is probably the simpler one. It's kind of just like an R type instruction, except for we have the immediate value here instead of a third register. And then the immediate value kind of takes the place of one of the register slots. What's important to know though, and this is why naming convention is so confusing. If you look at the add, we had RS plus RT equals RD. So these two get stored into RD. And if we look at the add immediate instruction, what's happening is we have RT and RS only. There's no RD. And so the result gets stored into RT instead of RD. And that's why this naming can be really confusing. But if you study it, you look at it, you can remember that the difference is that in an R type instruction, there's 3 registers. In an I type instruction, there's 2 registers. And it's always going to be the last register in your bits that you store the value into. Okay? So RT is where the value gets stored. Like here, T2 is our target register. That's where it gets stored, the result. And the last register in our bits here was RD, and that's where the result gets stored in an add. Here was T2. So come up with little tricks like that, maybe to remember it if you're not given this chart on your exam. But so you can see that it's a little bit different for the load word instruction. So a load word, how a load word works is an add is pretty simple. You add these two and store it into the first one. For a load word, we are loading a value from memory into a register. Okay, and the immediate comes in a memory offset. So load word S0, 0, S1. What this is saying is I want to load something into the register S0. And what I want to load is the contents of memory at this location represented by this 0 parentheses S1. And so what 0 parentheses S1 is saying is I'm talking about a memory location that is 0 plus the contents of S1. Is 0 plus the contents of S1. And I'm going to look, that's going to be an address in memory, right? And I'm going to look at that memory address and store it into S0. So again, don't get confused because the contents of S1 actually correspond to a memory address. It's not the value that you're storing into S0, it's the address in memory where the value you want is located. So for example, say our memory looked like this. This was okay, these are our addresses. This is 1A, 1B, 1C. And if we wanted to load whatever's stored in 1B, let's say that this is like 1010010100, some binary number, and this is 32 bits wide. Right? So our memory, each memory address has 32 bits of information in it. And what we want to do is we want to store this number. We want to load it into the register S0. So we do that. What we want to do is load word S0. And then the memory address that we want to get is hex 1B. Okay? And we can't type the memory address directly. We need to use an offset plus this register. So say that the contents of S1 were a hexadecimal 1B, which would be, that's a good example. Hex 1B is, we can break this out into bits and say it's 0001 for the one part, and then the binary representation of B. So remember, when we go into hexadecimal, we count normally up to 9. A represents 10, and B represents 11. So an 11 in binary is actually 8, not 4, 2, and 1. 8 plus 2 plus 1. 8 plus 2 is 10, plus 1 is 11. And that's a binary 11, or hex B. So this is a 1B in binary. So say that the contents of S1 are 0001, 1011. Okay? That's a hex 1B. So the load word, what we do is we say we want to load into register S0 the contents of memory at the address of 0 plus 1B, because we read this register value, and that becomes the address that we read memory from to load into load word. Okay, so load word is a little bit confusing, but make sure that you know that when you're in parentheses, you're dealing with addresses. When you're outside of parentheses, you're dealing with values. Okay, this is going to access memory and get a value, and you're going to load it into S0. But other than that, we have the immediate field. And so the immediate field is just whatever offset in memory you want to use. So we had a 4 here, we would do 4 memory spots forward from whatever address is specified here. And so you could use this for a loop or something. Say you change this value, and you'd be moving 1 spot ahead in memory or 1 spot back. Okay. Other things about the immediate types. Yeah, let's move on. So branch instructions are also immediate or I-type instructions. And branches are a little bit strange because so what a branch does, right? We're going to move execution to somewhere else. So BNE is a branch not equal. This is a conditional branch. These two types are conditional branches. So a conditional branch, if you remember, is, say we have our execution, like this is our code, right? This is our code, and then we have line 1, line 2, line 3, line 4. Let's say there's x equals 0. X gets added to 5, right? That's an instruction. And then we say if x is less than 5, then we go on to something else. And if we don't, then we go here, and let's just say x equals 6. 5, and let's say that this is line 12. So what this if is going to do is a branch. So when we get to this if condition, if this condition is true, then we go on to the next line. If the condition is not true, then we're going to jump not to the next line, but all the way down here. So that's kind of the idea of a conditional branch. And you've done this in C, C++, Java, whatever you've programmed in before. But we have to do it a little bit more directly when we're working with assembly code. So branch not equal is going to check if these two registers are equal to each other, and if they're not equal, then you're going to jump to the address specified by the label. So let's see. Yeah. Okay, so an address down here. So your address space, you have 32 bits. Sorry, that's not right. Yeah, okay, so your immediate field, you have 16 bits to work with, right? The problem is that your addresses are not 16 bits long, right? But you only have 16 bits to specify what address you want to jump to. So these are what we call relative jumps. Relative jumps. All right, so a relative jump will say that we're at line 6, and we want to jump down to line 24. Instead of telling the computer, I want to jump to line 24, we're going to say, I want to jump forward 18 lines. This is a relative jump. An absolute jump, or an absolute branch, they basically mean the same thing, would be we're at line 6, and then we'd say jump to line 180, right? That would be an absolute jump. Regardless of where we're at, we're going to jump to line 180. This one is just a relative jump relative to the base address. And so the advantage of using a relative jump is you can use fewer bits. This might be a smaller number, this relative jump. This might be a smaller number. So when we're constrained on space, we can save some space by using a relative jump. And the other thing that we know is when we look at our memory, right, we have words. So this is our addresses, and then this is our memory. And memory actually jumps up in steps of 4, right? Because we have 4 little blocks of memory or words that we can index into, but we want to be aligned to the start of the word, right? So this could be all 32 bits. Each one of these is a byte. But then the whole address, the whole word, would be 4 bytes long. So whenever we want to address into something, we'd want to grab the entire word. So we never want to start right here and then start reading. We're going to assume that these are all kind of just a continuous block, right? Now there are 4 bytes in there, but we just consider the start of them. So this is one address, the start of that. The next address will be 4 bytes greater than that. It'll be 4 steps greater than that. So say that this is hex 1A. Then the next one would actually be hex 1A plus 4. So A goes to B, C, D, E. The next one could be 1E. Okay, and these would all be binary, right? But you'd be jumping, and you'd be jumping by 4. So when we think about that, let's say that every address, we start at 0. The next one would be address 4. And we keep going, and we think about when we're counting by 4s in our address space, every address is going to be a multiple of 4. And that helps us out a little bit here, because when we're specifying an address, we can remove those bottom 2 bits and think only about the multiples of 4. Okay? Because we can't jump one address forward. One address forward would be like going within a word, and that's not allowed. So we can really only jump in multiples of 4. because the memory is word aligned. Okay, so by observing that, we can say that if we look at a binary number, this represents your 1, your 2, your 4, your 8. If we only jump in steps of 4, then there's no point in specifying how many copies of 2 and how many copies of 1 that we want to jump. We can only jump in multiples of 4. So what we do is we omit these last two bits in our immediate. And that's why there's two kind of dashes here. And what that lets us do is get 2 more bits on the higher end of our spectrum. So we would never be able to specify these 2 bits, so we're going to remove them and shift it down by 2. So if we wanted to jump forward 12 spots, so our immediate would be 12. In binary, that is 8, 4, 2, 1, 1, 1, 0, 0. Okay, this is a binary 12. What we would do if we wanted to put that into our immediate is we would cut off these 2 bits, and we would just put a 1, 1 preceded by the zeros. And then the processor would read this and say, okay, 1, 1. We know that there's a multiple of 4, so I'm going to add 2 more zeros on there, and this is a 12. So we're going to jump 12 spots ahead. So that's kind of how the computer saves these 2 bits of space. And what that gets you is, if we had to have 2 zeros here at the end to say this is a multiple of 4, then we wouldn't have these 2 bits on the higher end of the spectrum. So we could only, these 2 bits are the most significant bits. So they give us the greatest jump, the greatest range available, because these will let you specify up to like thousands of places, whereas these are just within 4 places. So by removing those last 2 bits, we save ourselves a little bit of space. So that's branches. We'll come back to branches. We'll do an example. And this jump is called this is an unconditional jump or branch, where there's no condition. When we do a jump instruction, we just jump directly to this label. So what we do is we and this is an unconditional jump, and it's also an absolute, sort of. Okay, it's a little bit complicated, but we'll get into that. So we do the same thing. When it's an unconditional, we don't need any registers to compare. We don't need anything to read from. We just give it the address that we want to jump to next. But when we think about this instruction, we still need the opcode. We still need to tell the processor how to interpret this instruction. There's 6 bits that represent the opcode. And then the other 26 bits are the address, and they call it a pseudo address. And the reason why is because our addresses is 32 bits, right? But we only have 26 bits to work with. We need to make up these 6 bits somewhere else, because there's 32 bits of possible address space, and we can only specify 26. So we don't have enough information. And we can use that same trick as before, as saying, well, we know that every address is going to be a multiple of 4. So every address is going to end in a 0, 0. So there's no point in specifying that 0, 0. That's just implied. We can just assume that it's going to be 0, 0. And so we can reclaim 2 more bits. So we have 26 bits to work with, plus the 2 0 bits at the end. So it's really like we have 28 bits. Okay, we're still missing 4. And there's no way around that. There's no good way around that. There's no way to specify information when you don't have enough bits to specify it. So what we do is we just grab whatever instruction that you're at. They take the top 4 bits and add them onto the front. So what that means is say that you're in your address space, and this is these are going to be binary or hex numbers. So okay, each one of these is 4 bits, and there's 8 of them, so that's 32 bits total. This is the address that we're at. The top 4 bits are represented by this most significant hex digit. That means there's 4 bits there, 0, 0, 0, 0. And when we were executing this instruction, say that it said to jump to some other address specified by 20 bits, say that this was what was in the immediate field. What we would do is we would take these top 4 bits, and add them on there. So 26 plus 4 gives you 30. And then we add 2 more zeros on to the end. Plus these 2 zeros gives you 32 total bits. So then that makes a complete address. So in that way, by using 4 bits of the instruction that we're currently on, and then ignoring those 2 least significant bits, we can kind of compress the 32-bit address into 26 bits so that we can use it in an instruction. So these are the 3 main types of instructions that I think you'll come across in this class. I'm not sure exactly what types of questions you'll see, but I would imagine that you might get something like decoding an instruction. So they give you an instruction like the add, and then they ask you to get the command in bits. Okay, so when you do that, you would need to have some kind of table that gives you the opcodes. I'm sure that you're not expected to memorize these opcodes because there's just so many of them, right? Like, look at all these commands, and these are the opcodes, right? And then for the R-type commands, you also have the function code on the end. So for example, an add has an opcode of all zeros, but a function code of 1 with 5 zeros. So let's do an example. We can decode an instruction. So say that our instruction was sub P3 T6 T7. So first off, what this instruction is doing is I'm going to say do the contents of T6 minus the contents, that's bad, of T7, and we're going to store that into T3. So an example of this is like if we called this X, Y, and Z. In normal programming, this would be X equals Y minus Z. Okay? But we're dealing with registers, so we have to be a little bit more specific. So first, for an R-type command, this is an R-type. We're going to have our opcode, which is 5 bits. We're going to have our 3 registers. 5, 5, 5. That's 20 bits. And then we have 12 more bits. Oh, this is 6 bits, sorry. 6-bit opcode. This is 21 bits. And then we have our 5 bits of shift, which we don't have to worry about in this class. And then our function code, which is 6 bits. So let's figure out how we place these registers, right? So first of all, the opcode for subtract, you'd look at some kind of table like this and you'd see subtract, subtract. Okay, the opcode is all zeros. So let's put in, our opcode is 1, 2, 3, 4, 5, 6 zeros. Okay. And our shift amount, we can pre-populate with 5 zeros because we don't have to worry about it. And then the other thing for these R-type instructions is a lot of them will have a function code. So our subtract, this was the opcode. And then here on the end is the function code. So 1, 0, 0, 0, 1, 0. Copy that down. 1, 0, 0, 0, 1, 0. Okay, and now we have the registers to deal with. So for an R-type instruction, look back up at the top here. It goes RD, RS, and RT. And then in the order in the bits, it goes RS, RT, RD. Let's first identify which is which. So in our code, this is our RD, RS, and RT. And so we're going to put them in this order. RS goes first, RT goes second, RD goes third. So this is the kind of crossover behavior you get. This is how the command is written, but then this is how it gets stored in the bits. So remember that for our registers, they always start with 0, 1. So then RS is our first one, T6. So then we put a 6 in binary. 6 in binary is 1, 1, 0. And that's 5 bits total. 7 in binary is 1, 1, 1. That's our 7. And 3 in binary is 0, 1, 1. Okay. So this would be our complete 32 bits of command. 6 plus 5 is 11, 16, 21, 26 plus 6 is 32. And one other thing that you might be asked to do is to write this in hex, because this is a lot to keep track of. So in hexadecimal, right, we group our binary digits or our bits by 4. And sometimes they're going to cross over between fields, but that's okay. So we're just going to group these into 4s, starting from the left. And you should end up with 4 bits on the end if you've done it right, because there's 32 bits total. Divide them into groups of 4, that's 8 groups of 4. So our hex command, we just look at each of these individually and convert it into hex. So 0 is easy, that's 0. 0, 0, 0, 1, that's a 1. 1, 1, 0, 0, that is 8 plus 4 is 12. All right, so we look at our table, we go, this is our decimal, this is our hex. Sometimes it's useful to draw a table like this. Up until 8 and 9, it's normal. But then we keep going, then we have to use the letters. So decimal 10 is an A, 11 is a B, 12 is C, 14 E, and 15 is F. Okay? So we have here a 12. Look at our table here. 12 is C. This is a hex C. The next one is 1, 1, 1, 1. That's 15, which is an F. 0, 1, 0, 1. That's 5, and 5 just goes to 5. 1, 0, 0, 0. That is an 8. 0, 0, 1, 0. That's 2. 0, 0, 1, 0. That's 2. So our final command would be hex 0, 1, CF 5, 8, 2, 2. And if you sent this command into a MIPS processor, it would perform the subtraction. Contents of T6 minus contents of T7 gets stored into T3. That's all we have to do. It's really just like keeping track of your registers, making sure you know which bits go where, and then looking at the table for your opcode and function code. Okay, so another thing that you might see is, this is just instead of using variables, we use registers in assembly programming, right? I'm pretty sure we've covered this. For register files, this is kind of what we look like. So when we're reading from a register, that also has to be done. There has to be hardware that accounts for that. And so it's not magic, but it's also not as complicated as it looks. So this is a register file. You might have seen an example of this before. So we have the write data, write address, and write enable, and then read data, read address, and read enable. So this allows reading and writing in this register file. And your register file on the MIPS processor is going to allow reading and writing because you can both store a result into the register file. That would be a store, that would be a write. Or you can read from a register file, which would be like, in most of your commands, you need to read a register value. So for an example, if we did add T4, T3, T2. We would first have to read the contents of T3 and T2 to get their values. And then the ALU would add them. We'd add the contents of T3 plus the contents of T2, right? After we've read the values. And then this gives us our value. And then we'd have to write it back into T4. So this operation is doing reading 2 registers and writing 1 register, even though it's neither a load word nor a store word nor nothing like that. So every command that uses registers is going to be using the register file in some way. So and I promise it's not as complicated as it looks. So the write data, that would be like our result. And let's pretend like we've already done the calculation. The ALU has already calculated what the sum of T3 and T2 are, and we're storing their T4. So the result, the sum of these two contents, is our result, and that's 32-bit number. And write address is the address of the register. So for T4, I guess this is just a 2-bit one, so let's call this T1 instead. Okay. So our write address would be a binary 1, which is 0, 1. And that's telling us that we're going to be accessing register 1. And write enable would be 1 saying, yes, we are going to write to register 1. Okay. And the next thing is that the data comes in here. It's on this line. So this slash means that there's 32 individual wires here, basically. And it's going into this this register. And this is kind of like the flip-flops that we studied for the last exam, I think, right? Where you have a clock pulse and a load signal and then your data coming in. So this is a decoder. If you remember decoders, I think I have, yeah, if you remember decoders, you have a binary number as your input, and the output is 1 hot. So say that we want to access register 1, we pass in a binary 1, and then the output of that is going to be a 1 hot vector, where it's 1 for register 1 and 0 for the other ones. So these signals will be our load signals. And so you can see that a 0 means that we're not going to do anything with register 0, so this one stays locked. We are going to load into register 1, but then these other two also stay locked. So none of this data can access or change these registers. Only this register is going to get changed. So on a rising clock edge, the data coming in, which you can trace with your pencil here, enters into this register and will get latched in by this clock pulse. And that's all it is, really. These buffers, we'll do the read next. Okay, do I have a... Yeah, this is a better example. So what these buffers do is basically either break the circuit or open the circuit. They're kind of just like a switch. So the truth table logic for it is you have a control signal that comes into the top. If that control signal is 1, then X gets passed through to Y. If that control signal is 0, then Y is what we call high Z or disconnected from X. So it's like it's an open circuit. So it's really not that complicated. It's just you either connect it or you don't. So in the next example, let's do a read from the register. This is a bad example. Let's do, I think, the next one. Yeah. So an add immediate T3, T2, and T8. So again, what this command is doing is we're going to say the contents of T2 plus 8 gets stored into T3. Okay, and add immediate. So we're adding this one plus the immediate, which is 8. So this is a 3-bit decoder. And we're going to be, let's look at the memory read. So T2, we first have to get the contents of T2. So the way that we do that is we're going to go to this read address. So read enable is going to be 1. We are reading something. And write enable for now will be 0. We're not writing anything just yet. So read address, we have T2 that we need to read from. So this is going to be a binary 2, which is 0, 1, 0. And again, if you're struggling with binary, it's going to be asked of you to know binary at this point. So do some practice converting between binary and back. And I promise for little numbers, it'll become like riding a bike. You can't forget it after a while. So read address is 0, 1, 0 because we're going to be accessing register 2. And because this is a decoder, that's going to mean that there's zeros on the outputs of all of them except for the output number 2. All of them are zeros. And what these zeros do, if you can see, they go to the control signal of these buffers. So remember, if the control signal of the buffer is a 0, then it's like the output is disconnected from the input. So what's coming in on each of these lines is whatever is stored in this register. It's sitting right here on this buffer, but because the control signal is 0, there's a break in the circuit, so it doesn't get passed through to this side, to the actual read data. Okay? It doesn't get passed through. What happens is, like this one is broken, right? Please read for that. So whatever data is in this register, it's sitting on this wire, but it doesn't get passed out through to the read data on our outputs. This is where our output is going to be on this line. The only one where it does pass through is on D2, where the control signal here is 1, so that connects the output to the input. There's a connection there. And that means that the data from T2 is sitting on this wire, which is connected directly to our output, our read data. So this is going to have the contents of T2. And all of these other ones, because the outputs of the decoder are 0, they're all going to be blocked. So that's really how it works. That's really how the memory is working. And if you can understand this, then you're really going to be one step ahead to understanding the MIPS processor in general, because it's basically all about tracking the control signals and then tracking what happens when those control signals are set. So here we have a 1 that's closing this buffer so that we can move the data from T2 out into our output. So that's how the read works, and we went over how the write works. Another thing that you might see, and that's really useful for MIPS, is the to read register file. So for an example, if we're doing an R-type instruction like add, we have to read the contents of T2. We have to add the contents of T3. That's 2 reads, and then store that into T1, right? And it is a lot quicker if we can do those reads in parallel. So we're going to do them at the same time. And the only difference is that instead of just connecting whatever wires specify T2 into the read 1 address, we're also going to connect the read 2 address. So for this example, read 1 address, let's call this, this would be RD, RS, and RT. So this one, let's call R1, let's call that RS, RT, RD, right? This is where the result is going to get stored. So RS is T2. T2, for our inputs, we're going to have a binary 2, that's 0, 1, 0. And it's going to work the same way. It gets decoded, only unlocks that value that we need, and passes the value of register 2 to the output. T3, that's going to be a binary 3 for our signal, so 0, 1, 1. That's our address, which means that this one, only D3 is a 1. All the rest of them are zeros, which means these things are blocked out. The contents of this register does not get passed through to your output line. And then once you have the contents of your 2 registers, then your ALU will operate on them and then store them back, doing a write. So when we're doing the write, we would have the write and enable set, and the read enable would have been set for these 2. This allows us to write. And then our address here would be, we're writing to T1. This would be 0, 0, 1, which is a binary 1. And then we load, this would be a 1, and all the other ones would be 0. That enables this, this register to load in the data, which is your result. So these 2 would get read out, and the ALU would add them. This is your result. And that would go all the way back to there. And then using the same logic, the write address will allow that write to enter into this register. So you can do more examples like this. I hope that you would have access to something like this either in your book or in your professor's notes. But now we get into a couple of the other components. So for a processor, we need the CPU, and like the ALU is going to do the arithmetic operations, so the calculations, the multiply, add, subtract, divide. And not only if you're using an add command, but for example, in load word, we have, let's call this P2. In a load word command, you still need the ALU because you need to do 4 plus the contents of T4. And then this is your memory address. So the ALU is used not only for add and subtract and mathematical commands, but some commands you need to use the ALU to perform in addition, just to get to the right address. So this is the memory address offset calculation for a load word. And then we would add these 2 things together, and then we would go look in memory at that location and store the result into T2. Okay, memory, we have instruction memory and data memory. So Harvard architecture, I don't know if you've learned these terms, but a Harvard architecture is where we have separate blocks of memory for instructions and for data. And a von Neumann architecture is where instruction and data memory are in the same block. They're just indexed into differently. So you'd have to be careful about knowing where your instructions end and your data starts, and then if there's more instructions after that, and then more data after that. But the von Neumann architecture is what we end up using in a lot of cases. And a RAM, a random access memory, I think we talked about that in our last class, for the last exam as well. So for processor design, interrupts are useful. Did you guys talk about interrupts in your class? Maybe. Well, interrupts allow for a peripheral to kind of grab the attention of the processor. And we don't have to worry about that for MIPS. MIPS is pretty simple. So here's like the single cycle processor. We don't have to worry about interrupts, but you'll see variations on this single cycle processor that allow for interrupts. Maybe they allow for more different types of like conditional jumps or unconditional jumps, things like that. This is the basic single cycle processor design for these instructions. But the program counter. So the program counter is important. It points to the next instruction. So when we're operating on, let's say that we're at address. These are our instructions. Okay, and we're operating on this instruction. The program counter is always going to point towards the next instruction. Because once we know what the next instruction is, we can grab that and load it in as soon as we're done with the instruction that we're working on. So the program counter tells you where you're going to go next. And if you do have a jump, then the program counter won't say this next instruction. Let's say that this instruction is a branch and the condition is true. Then the program counter would then point to wherever we're branching to. So it might be 2 instructions down, but it might be way further. So the program counter always stores where you're going to go after you finish executing this instruction. So the ALU, of course, does the mathematical operations. There are different ALU flags that I don't think you have to worry about for this, but maybe you've seen these, the 0, carry, negative, and overflow flags. And these will let you know if your operation, has produced an overflow. Sometimes if you're working with binary numbers, your results will exceed the maximum allowed in that set of bits. So an overflow will tell you when your operation was too big to store in however many bits you have. So if your addition leads to a number that's bigger than the maximum, then you get overflow. Or if the value is negative, these flags can be useful. But I don't think you have to worry about them for this, but maybe you'll see them. And then your ALU is doing all sorts of things, all sorts of mathematical operations, and also comparisons and bitwise operations like OR and that's done in the ALU. The sign extender is a little tricky, but it's not that difficult to understand what it's doing, but it's kind of tricky to understand why. So we find that a lot of times for our immediates are 16 bits, but our addresses and everything are 32 bits. So for an example, for a branch instruction, like a branch equal BEQ, we would have say R1, R4, and then our offset. So if R1 and R4 are equal to each other, then we'll jump this many spots forward. And we'd have the current address, which is 32 bits. But if we know that the opcode is 6 bits, these two together, the two registers, are 10 bits. That's 16 bits out of 32. That leaves 16 bits for the immediate or for the offset. But we need to specify an address of 32 bits. Well, what we do is we can add the offset, current address, plus the offset, and that'll be our new address. Right, that's the idea of a relative jump. But the current address is 32 bits. The offset is 16 bits. And we can't necessarily add those two together, especially if they are signed. So if you remember 2's complement, 2's complement makes things a little bit weird when you're adding and subtracting. But if they're not the same number of bits, then their 2's complement representations won't agree. So the sign extender makes sure that your immediates get sign extended to 32 bits so that you can add and subtract with the other things like the instruction and the data that are already 32 bits in a signed format. So the sign extender is really important if you're working with signed numbers, which MIPS allows. You can have a negative offset. So instead of jumping forward, you can maybe jump back 3 instructions. So the sign extender allows for the immediates to play with the other types of data. So let's look at, there's one more concept before we jump into examples. Pipelining. So pipelining is a little bit more advanced and it requires some additional hardware, but pipelining conceptually allows you to execute multiple instructions at the same time. So the MIPS architecture that we're looking at is the single cycle processor. And that means that every time your internal system has a clock. So your clock is going at a certain rate, and every clock pulse means one instruction is done. And that's the single cycle processor. It means every clock cycle, you get one instruction done. And that's nice. That seems pretty efficient. But what if one instruction takes longer than another instruction? Well, you could do the slow instruction in one cycle, but the fast instruction also takes an entire cycle. So if you were to speed up your clock, you would be able to speed up how fast you're doing your instructions, but it would be the same speed increase for every type of instruction. What you can do is, instead of having a single cycle, you can break it up into more cycles for each instruction. So with each clock cycle, instead of doing the entire operation, you do a piece of it. So these are 5 common ways to, this is one way to split an instruction into 5 steps. So the instruction fetch is where you grab the next address, you grab the address of the instruction that you're at, and then you increment the program counter to the next step. And then the instruction decode and register fetch is where you use the control decoder to figure out like what's the opcode. That's what would happen in this step. You activate the ALU, so that's where you'd be looking at the function of the ALU, whether it's an add or a subtract or a compare. And then you also grab your registers. So that's in the fetch stage. Instruction execution. This is where it kind of branches based on your type of instruction. So for an R type, like an add or a subtract, your ALU output is the result of your operations. So your ALU will actually calculate in this step the result. For a memory reference, like a load word or a store word, you use the ALU to compute that memory offset. For branches, right, you'll check that condition to see if the condition is met. And then for a jump, you have to do that kind of bit saving measure of adding on those 2 bits on the end and then copying the top 4 bits from your instruction. So in the execution, that means different things for each type of instruction, but they're all executing something. And most of them are using the ALU for that. So by breaking the execution into these little steps, we can have one instruction in the fetch stage. And then when that instruction moves on to the decode stage, we can fetch for the next instruction. We can do them at the same time. So what we would need to do is, right now we have, say this is our CPU clock. Okay, and that's just a square wave. This is one cycle. This is one cycle. So in each cycle, we could perform, maybe let's say we do an add here, and then do a load word. But if we wanted to use pipelining, we would need to have a faster clock. Let's say that our clock rate is now like this, it's much faster. And 1, 2, 3, 4, this is 5 cycles. So maybe for this first clock cycle, we do fetch 1. And then in this second clock cycle, we do, what was it, decode is next? Yeah, instruction fetch, instruction decode. We're going to decode for instruction number 1, but then we can also use fetch for instruction 2. And then in this third cycle, we could do execution for instruction 1, decode for instruction 2. We're talking about this clock cycle right here. And this one was fetch, This was fetch and decode. And then now we could do execution for the first instruction, decode for the second instruction, and we could fetch a third instruction. And so you can see how if we pipeline, we can layer these things on top of each other. So we can finish these things a lot quicker. We don't have to wait for an instruction to do its fetch, decode, execution, write back, and memory write back. All of those steps. We don't have to wait for all of those cycles. We can start working on the next one while the first one is still executing. So that's the idea of pipelining. We can kind of layer these things on top of each other. And I think there was a really good diagram that kind of showed it in terms of laundry. So, for laundry, like you have to wash your clothes, dry your clothes, and then fold them and put them away. This is like a single cycle processor. So one cycle would be doing all of those steps, and then you start on the next set of steps. With pipelining, you have basically breaking it into steps. So we have fetch, decode, execution, and then I think they call it data write back and memory write back. There's different ways to break it up. Yeah, memory access, let's call it memory and then write back. So sorry about this. Okay, so these are kind of our 5 different steps. And here we have, wash, dry, fold, put away. The same principle, really, where we can do wash for our first batch. And then while it's drying, we can start washing the second batch. And then we can fold the first batch while the next one is washing and then the other one is drying. And you can see that if we're doing these 4 instructions, we can finish it in a fraction of the time as we were waiting for all of the steps to finish. So that's the idea of pipelining. Now, pipelining doesn't work on a single cycle processor out of the box because there's no way to have 2 different commands in execution at the same time in a single cycle machine. So the single cycle machine would need a little bit of additional hardware to separate those stages from each other, and it would need a faster clock to cycle once for each of those stages. Okay, but that's the idea behind pipelining. I don't think you actually have to look too much at a pipelined machine in this class. That's kind of a computer architecture thing, but the concept is pretty intuitive if you see an example. So the next thing we can do is actually trace the bits through an example of a single cycle machine execution. So this is probably one of the most confusing things that students have trouble with, but I promise that if you understand everything up to this point, and if you understand how a mux works, then you're basically there. So let's take a command. Let's take an add immediate command. So an add immediate command. Okay. It adds the contents of T4 plus 75 and stores it into the register T3. The first thing we need to do is let's break this down into bits. So remember, we're going to have our opcode, our RD, or sorry, I think it's RS, RT in this case, and then our 16 bits immediate. This is 6 bits, 5-bit, 5-bit, and 16 bits. Now let's double check the add immediate down here. So it's an I-type instruction. And so they call it RT and RS. So RT is the first one, and RT goes second in your bits. RT is the first one, RT goes second in the bits. So yeah. So this is our RT, RS, immediate, op. So we break this into bits. Let's look at our opcodes. We have an add immediate. We look at our table, and your table might look at something different from this. But our opcode is 001100. Okay. So 001100. RS, that's T4, which is a use a different color. Okay. For our registers, it's always 0, 1, followed by your register number in binary. So T4. 4 in binary is 1, 0, 0. Okay, so that's our 5 bits. RT is T3. So that's 0, 1, followed by 3 in binary, which is 0, 1, 1. And then our immediate. Our immediate is 75. So let's convert 75 to binary. The way that I like to do it is think about your powers of 2. So if we think about our powers of 2, 32, 64, 128. 64 is the biggest power of 2 that's less than 75. So we can say that 75 equals 64 plus, well, 75 minus 64 is what, 11? The next biggest power of 2 before 11 is 8. 12 and 8. We subtract an 8 out and we're left with 3. That'll be 2 plus 1. So we can represent it as a sum of powers of 2. Yeah. And then when we look at our binary, each place value is represented by a power of 2. So this is 1, 2, 4, 8, 16, 32, and 64. So our 75 is 1 copy of 64, 0 copies of 32, 0 copies of 16, 1 times 8, 0 fours, 1 times 2, and 1 times 1. This is how we represent 75 in binary. And of course, it'll be 16 bits, and this is 1, 2, 3, 4, 5, 6, 7 bits. So yeah, there's 7 bits. So we need 9 zeros before that. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 0, 0, 1, 0, 1, 1. So I believe, unless I made a mistake, that should be yeah, that should be 75 in binary. So whatever, it won't make much of a difference. So we've got our bits. And then one more important thing to do is this is 32 bits long. So these bits are 31 through 26. Right? These ones are 25 to 21, 20 to 16. And these are 15 to 0. And take a second and verify these. You understand that 15 minus 0 is 15, but bits 15 to bits 0, inclusive on both sides, is 16 total bits. It's the off by 1 stuff that throws people off all the time. But if you can identify these ranges within the string, then we're ready to go. So let's look at what happens. So the first thing is, when our program counter is pointing to this instruction. So let's say that this is at address 48, okay? So when this instruction comes up, that means that our instruction address is 48. So our program counter is pointing to 48. So we grab bits 31 to 0. That's the entire instruction. Bits 31 to 0, that's all of the bit fields. So those bits are going to be on a wire right here. This is a 32-bit wide wire, right? So we grab instruction address 48. And then what happens? Well, program counter also splits over here. This is a 32-bit number. We add 4. And the output is the address of the next instruction to execute. So if our address is 48, 48 plus 4 is going to be, excuse me. So 48 plus 4 is 52, right? Well, we're dealing with hex, so it's not that simple. What we really need is hex 8 plus 4, which is 12, right? And 12, if we think about our numbers, remember A is 10, B is 11, C is 12. So it'd really be 4C. So the first step is always that the program counter gets updated. So our next program counter is going to be 4C. And then what happens to these bits? Well, 31 through 26 flow into control. What is 31 through 26? If we look down here, that's our opcode. So all this bit is saying here This is our opcode. Our opcode is going to flow into sum's control structure, which looks at your opcode and then determines how to handle the rest of your control signals from there. Where do the rest of the bits go? Well, 25 to 21, which one were those? 25 to 21, that's our RS. RS. 20 through 16 is RT. And then 15 to 11. If we look, 15 to 11 isn't really anything. You know, it's like the first half of these bits. So this little box here, 15 to 11, that's for a different type of instruction. 15 to 0, that's our immediate. Those are going to flow into our sign extender. And that allows us to add and subtract them with other 32-bit numbers. So let's think about kind of in the stages, right? Instruction fetch. We fetched this instruction from memory and we got all 32 bits of it. Now instruction decode. So the opcode goes into this control logic. It's not really important that you know what the hardware of this looks like, but as long as you can figure out what these control signals are from this whole process. So our instruction is an add immediate. So what we want is the contents of T4, and we need to add it to the 75, which is our immediate. So T4 is our RS, and T3 is our RT. And if you think about what's happening to each of those, we're going to read from T4, because we need to get the contents of T4, add it to 75, and then we're going to write to T3. We never need to write to T4, and we never need to read from T3. We only need to read from T4, and then write to T3. So we look at our, sometimes you'll have like a write enable on your register block. But in this case, I guess they don't. But RS, so our RS address is going to be, that's T4. So RS is, let me see if I can make this pen a little bit smaller. RS is going to be, call it a hex 4. And RT is hex 3. So we would have, and I guess it doesn't matter for this case because the other muxes are set up. So read data is going to be the contents of R4. And read data 2 is going to be the contents of R3. Okay? So what happens? We need the contents of R4 to get added to the 75. So let's look back at the 75. So this immediate, that's our 75. It's all in bits. It gets sign extended. And if it's a positive number, sign extending just means that we add zeros out front of it. So this is still going to be our 75 on the other end of the sign extender. And we want this 75 to go into the ALU. And we also want the contents of R4 to go into the ALU. And we want this to add. Okay? So if we want 75 to go into the ALU, then this mux has to select this bottom line. Okay, here's where the control signals come in. So if we want this input of the mux to go and not this one, right, because we didn't even care about reading R3. We don't want the top one, we want the bottom one. So this control line, ALU select, has to be 0 because we want the 0 input. And that'll put our 75 here and our contents of R4 there, and they'll get added up. This is our sum. And the next thing we need is we need that sum to get stored into T3. So we're not writing it to memory. In an add immediate instruction, this result gets stored into the register, and we haven't touched memory at all. So you might think about your memory block as kind of being useless in this instruction. So we can disable it by setting these enable signals to be 0. If it was a load word or a store word, then we would be loading or storing from memory, and then we would have to either write or read. But in this case, for an instruction that doesn't deal with memory, it's just doing things within the register file, then we can have our enable set to 0. So our sum, we need that to end up here in our, here in our write data. Because we want, again, if we remember our register file, our write data, and then our write address, and our write enable, they allow us to store a value into this register specified by write address. So we want our sum to come into this write data thing. So if we follow this line, there's a dot right here, which means this is connected. So our sum is coming in here to this mux. And we want it to pass through to the right data. We want our sum to get written into the register file at address T3. So we want the mux to choose this bottom path and not the top path. Remember, because we didn't even read anything from memory. So this is going to be garbage, nonsense, or nothing. So we want this to be a 0. We want this to be a 0 because that'll select this bottom path on the mux. So that means that once that control bit is set, our sum comes back here to the right data. Okay, so that one is covered. When it gets back to the right data, we need to make sure that our right address is correct. So our right address is going to be, we're writing to T3. So that's going to be the address of T3, which is our RT. That's going to be bits 20 through 16 of our instruction. So 0, 1, 0, 1, 1, right? 20 to 16. And if we look at the options for this mux has bits 20 through 16 coming in on this side and 15 through 11 coming on this side. So this set of bits is for an R-type instruction where there's 3 registers. This would refer to the 3rd register. But because we aren't dealing with an R-type instruction, we don't want this mux to deal with these bits because these bits are nonsense. They don't refer to a register. They're part of our immediate. So we want to select this path instead because bits 20 through 16, we need those to go to the right address because they say the address of T3. We want to write this sum to T3. So we want the mux to select this one, which means that this control signal, we trace it back to the control block, register file, write, address, select. We need that to be a 1 because we need to choose this top path. Okay. Yeah, and these other control signals that come back, so like this one needs to be 0. This one needs to be 0. It's just we trade these lines. Okay. And now we have our right address set. So this is going to say the address of T3, and the sum is calculated. That's going to get stored in there. So everything is good. Let's see, do we meet it? Oh yeah, write enable. We need to write to the register file, so that should be a 1. And the ALU operation. So this one's a little tricky, but it depends on your implementation. But the ALU operation has to be something that tells the ALU to add instead of subtract. So I wouldn't worry too much about the ALU op, like the exact bits, because without a table of the implementation, you're not going to know what those bits should be. But the ALU op is going to be some set of bits that tell the ALU to add these 2 numbers together instead of subtracting them or comparing them. So there we've looked at all the control signals. We reasoned out logically how the bits should flow. And we looked down here and we figured out what they're talking about when they say, IR 31 through 26. Those are the top 6 bits that refers to your opcode. So you can kind of see how the opcode is what's doing this control. And you can convince yourself too that if you were to change the registers, but keep the opcode the same, all of these control signals would still have to be the same way. So the opcode determines which muxes go one way or the other. And that's determined just in the opcode. The values of the registers aren't going to affect whether you're adding here or whether you're reading from data. That's all going to be controlled in this opcode. So the opcode determines the mux values, and then the registers will get added and stored back in. So I think there's, this is one example. This is a really good practice. You might have to do this on your exam. If you understand this, great. You can also check out, there's other videos for previous semester exam reviews as well, where we do similar things like this. Maybe you did a different command. But definitely make sure that you understand this diagram, or at least how to read it. I think we'll probably finish up here with some questions. And I don't know if you have these in your notes. I think these came from Dr. Kogan's notes when she taught this semester when she taught this class in previous semesters. So a couple of questions just to test ourselves. Why is this architecture called a single cycle machine? So if we look at this, there were no clock pulses in the intermediate stages of the execution. Everything kind of was just flowing through bits, flowing through muxes that was already calculated. That's why it's a single cycle. There's no this result waits here until there's a clock cycle, and then it gets latched into the next thing. That doesn't happen here. If we did pipelining, if we did a multi-cycle architecture, then maybe we would implement something like that. But a single cycle machine basically just takes one cycle to execute any instruction. That's why it's called a single cycle machine. What is the difference between instruction and data memory? Well, in a Harvard architecture, they are separate, distinct sections of memory. In a von Neumann architecture, they are the same block of memory. But instructions, of course, code for instructions, and data is data. It's the way that you interpret them. The program counter always points to the next instruction to be executed. That's really important. Why does the CPU need a sign extender? This is so that we can add our immediate values to either data memory or the contents of registers. So for in this example, right, our 75, it was a 16-bit number. Whereas the contents of register 4, this is a 32-bit number. So in order to add them, we need to sign extend the 16-bit number into a 32-bit number. And then that way we could add them bit for bit, and they would work nice together. Okay, so that's why a sign extender is needed, so that we can deal with those register immediates, the immediates that aren't 32 bits long. A branch address, that's kind of like so the branch address is calculated using yeah, so the branch address is a relative jump. So the example here given is we are at address 20, and we need to go to address 84. So we're at 20. We want 84. And so what's done in hardware is you look at the program counter and you add to the program counter to make it be 84. So if we're at 20, we know that the PC always has the next instruction. The program counter is going to have 24. That's the next instruction because it always goes in bits of 4. And so if we want to know what our immediate should be for this branch instruction, if we want to go to 84, we would add 60 to the program counter. So that's what's going to be calculated inside the machine. So you would put an 84 here, and it would calculate, okay, we're at instruction 20. The program counter has 24, so we're going to do a 60. Okay. So you need to make sure that you specify that correctly. But that's how the branch address is calculated. Don't forget that -4. That's because the program counter already has that +4 inside of it, because it's already pointing to the next instruction. A jump address is calculated. Remember, a jump address is an absolute address in a way, where you have 32 bits of total address space, but the jump only has 26 bits. So you grab the top 4 bits from your current instruction, and you add it on the top, and you add 2 zeros onto the end. 26 plus 4 plus 2 means that we have 32 total bits for the next address if you're jumping. What is the role in the ALU in an R-type instruction or an I-type instruction? An R-type instruction, right, if we are doing an add or subtract, then the ALU is going to do that adding and subtraction. In an I-type instruction, it sort of depends. For example, this add immediate was an I-type instruction. We did adding here. But if you're doing a load word or a store word, then the ALU would be used to calculate the memory offset. So I think we saw an example of that where if your offset is non-zero. How is the ALU used in load and store instructions? Yeah, that's where we have like store word, T4. So the ALU is used to calculate this memory location, and then we would store this into that memory location because it's a store word. So this is the offset. This is the register that contains a memory address. You'd go this contents plus 8. Then that's your memory address, and then you would store into that memory address. Okay. But why is a mux needed at the register block write address? So if we look back at this, register block write address. They're talking about this one. We need a mux here because if we're doing an immediate type instruction, we're writing to the second register. But if there's an R type instruction and there's 3 registers, we're going to write to that third register. So it's for I type and R types. Why is a mux needed on one of the ALU inputs? So that's here. If we have if in an add type instruction, we would be reading 2 registers and adding them together. So we would want both of these. We want this read data to flow through. Or for an immediate type instruction, we want the immediate to flow through. So we have to choose between either another register or the immediate, depending on certain types of instructions. And finally, why is a mux needed between data memory and register block? So that's here to determine whether we're, excuse me, whether we're storing the data that we read or the output of the ALU. My voice is going, so we'll end it here. Oh, goodness. Any questions? Okay, if there's no questions, then stop the recording here. Message on Discord if you if you have any further questions. Otherwise, good luck on your exam.